All right. Okay, we'll go ahead and get started. Hello, all of you on Zoom. Okay, I decided to, on Mondays and Wednesdays, I just sent out a Zoom invitation to everyone. I've been having people say, I want on your Zoom and I want off your Zoom list, invite list, and I didn't want to miss anyone. Okay, so Mondays and Wednesdays, it'll be both on Zoom and in class. Fridays will be all on Zoom. Okay, so I'm going to share my screen. Oops. Go back. Share. Okay, there we go. Okay, can you all see the screen?
Yes.
Okay, great. Okay, so I'll quickly review structure and stereochemistry of alkanes. I don't have the clicker questions written yet for Top Hat, but I hope to have some by Wednesday. Okay, so these are the 4 classes of hydrocarbons, and in this chapter we're looking at
Try to have a nice.
we're looking
It's
at
not cold
alkanes.
for once, but no.
Okay, go ahead and mute your microphone. Alkanes, as long as there are no rings, we'll have the general formula CnH2n plus 2, where n is a positive integer. Okay, so if I had 12 carbons and no rings, then we would expect to have 26 hydrogens. Okay, 2 times 12 plus 2. The main source of alkanes is natural gas and petroleum. The dominant intermolecular force for alkanes is London dispersion, which is very weak. It's a very weak intermolecular force, and so there's not a lot of attraction between these lighter alkanes. And so they're gases at room temperature. You have to get them pretty cold in order to get them to form a liquid. Liquid methane boils at minus 160 Celsius, for example. Propane can be liquefied if it's put under pressure. It can be put under pressure, converted to a liquid, and then it can be shipped in propane tanks. Okay, these are the first 4 alkanes: methane, ethane, propane, and butane. These are all gases. When we get to 5 carbons, then pentane is a liquid. Okay, so you will need to know from memory the names of the first 10 alkanes through decane. We talked about isomers. There are actually several different types of isomers. This is one that's called constitutional or skeletal isomers, where we change the way in which the carbons are connected. Pentane has 3 constitutional isomers. And these are the common names. Okay, for testing and homework purposes, I'm going to ask you about IUPAC. We introduced IUPAC last time. And sure I'm on screen. Okay. Okay, so the first one is just called pentane. It may be called N-pentane for emphasis. The lowercase n stands for normal, which means just a straight chain. But pentane or N-pentane mean the same thing. Okay. All right, the next one is what we call isopentane. And in the IUPAC, the longest chain is 4. 4 corresponds to 1 alkane. It was on the previous slide. 4 carbon alkane is butane. Okay, good. And we were introduced to the IUPAC or systematic method last time. Okay, and then this branch we get by taking methane, pulling off a hydrogen and sticking it on the parent chain. So that's a methyl. And it is located on position number 2. Okay, so we would call this 2-methylbutane. This is the IUPAC, and then isopentane is the common name. All right, this is neopentane, which is shown on the screen. I've shown the line angle formula here. And in the IUPAC, okay, this is the main chain right here. Okay, 3 carbons is 3 carbon alkane is what? Propane. Good, propane. Okay, and then on carbon number 2, we have 2 of these methyls. Okay, so this is, we have dimethyl. Okay, you do need this prefix. Okay, so this is dimethyl propane. Okay, and then this is important. Every substituent gets a number, even if it's the same substituent on the same carbon. Okay, so this is 2, 2 dimethyl propane. Okay, you have to have both 2's. Okay, for this one, we want to give it the lowest possible number. Okay, so the way I've got it written, we want to start numbering from the left. Okay, it would not be correct to go this way and call it 3-methylbutane. Okay, we actually, we definitely need the IUPAC or systematic method of naming, especially even when we get to 6 carbons. I'm going to go ahead and draw those. Sure that's on screen. I think it is. Yep. Let me bring it down just a little bit. Okay, and the next one would be, oops, I got too many there. Okay, 1, 2, 3, 4, 5, 6. Okay, so with C6H14, we've now got 5 isomers. And even at this point, if we were to give every one of these a common name, it would get very cumbersome. Okay, but we can apply the IUPAC rules and name each one of these. Okay, so this one, of course, is hexane. Or you could say N-hexane, either one. Okay, so here we have 1, 2, 3, 4, 5. That would be pentane. And we have a methyl group here. So that's 2-methyl pentane. What would this one be? 3-methyl pentane. Good. 3-methyl pentane. And this one would be 2,2-dimethyl butane. Okay, because now our chain is shortened to 4. And this would be 2,3-dimethyl butane. All right, if we have a 2-carbon branch like this, okay, that is based on ethane. Okay, if we take ethane, CH3, pull off the hydrogen, stick it on the main chain, this is now an ethyl. Okay, so this would be, and that's pentane. And this would be 3-ethyl pentane. Okay, it would not be correct to call this 2-ethyl pentane. Okay, why not? Why is 2-ethyl pentane? This is 3-ethyl pentane. That is not 2-ethyl pentane. That's not the correct name.
The longest chain goes from the top to the
Good, good. Pentane is not the longest chain. Okay, so the longest chain is 1, 2, 3, 4, 5, 6. Okay, so this would actually be 3-methyl hexane. Okay, and again, we want a number from whichever side gives us the lowest number. So again, it would not be correct to call this 4-methyl hexane. Okay, if I told you to draw 4-methyl hexane, you could do it, but it would not be the correct name. Okay, this is hexane, 2, 3, 4, 5, 6. And got a substituent on the 3rd carbon. What is this substituent? Okay, 3-carbon alkane is what? Propane. Yeah, but this is connected to the middle carbon. It's called isopropyl. Yeah. Isopropyl. Okay, so 3 isopropyl hexanes. Okay, this is a propyl group. Okay, see the difference? Okay, you got a 3-carbon branch, but propyl, also called N-propyl, is where it's connected to the end carbon. Isopropyl is where it's connected to the middle carbon. Okay, so this is 9 carbons. This is called nonane. Okay, so nonane. And 4, 5. Okay, this one would be 5 what? Nonane. Okay, you got 4 carbons. Okay, 4-carbon alkane is butane. Okay, so this is a butyl. Or you could also call it N-butyl. Okay, again, we have 4 carbons, but instead of the first carbon attaching to the main chain, the second one is. Okay, so this is called sec-butyl. no name. Okay, and then we have two that are based on isobutane as a substituent. If we were to remove one of these carbons on the end and attach it like this, this is isobutyl. I remember it this way, that's an isopropyl, and it has an extra CH2. In fact, if we add another carbon like this, if it's branched at the opposite end, we've got 5 carbons. So this is now isopentyl. That's an isopentyl group. Let's see, that may not be the longest chain anymore. Let me see. 1, 2, 3, 4, 5. Well, yeah, I think it is. Okay. Okay, and then the fourth group would be if we connected it to the middle carbon like this. Okay, and this is called a T-butyl or tert-butyl. So this is 5 tert-butyl nonane. Or it's also just sometimes called T-butyl. Okay, lowercase t. Okay, alphabetizing. Okay, if you have different substituents here. All right, so this is 1, 2, 3, 4, 5, 6. So that's hexane. That's the parent. And then we have, okay, start from this end. All right, so this is 3-ethyl. And then we have 3,4,4 trimethyl hexane. Okay, in alphabetizing, we ignore the multiplier prefix. Okay, in this case, it wouldn't make any difference. But if we had a triethyl and a methyl, for example, the ethyl would still come first. There's a lot of crazy rules as far as alphabetizing. Okay, for example, in sec-butyl and tert-butyl, those are alphabetized under the V's. And if you look it up in a handbook or a catalog or like a chemical supply catalog, you'd find tert-butyl 3-tert-butylhexane or whatever it happens to be under the B's, not under the T's. And then isobutyl and isopropyl are actually alphabetized under the I. Okay. I'll give you a little bit of slack on that, but you do have to name these correctly and number them correctly. Okay, every substituent gets a number. Numbers are separated by commas. Numbers are separated by words by a hyphen. Okay, and once again, these are some of the common alkyl groups. Okay, so this one has the longest chain as decane, and so we would lump these all together, 2,5,7-trimethyldecaine. Okay, the reason I put it that way, we wouldn't say 2-methyl, 5-methyl, 7-methyldecane. We just lump all the numbers together for the same substituent. Okay, so these are iso groups. Isopropyl. Okay, and then if we insert a CH2 between the isopropyl and the parent, that's an isobutyl. If we insert 2 CH2s, that's now an isopentyl. The older name is isoamyl. You may see that commercially. There's a product called isoamyl alcohol, for example. And then if we added another CH2, that would be isohexyl. Okay, so here are 4 isopropyl and 5 tert-butyl, 4 isopropyl octane. Octane is 8, and 5 tert-butyl decane. Okay, these are the multiplier prefixes. Okay, ditri, tetra, penta, hexa, hepta, and so on. Okay, complex substituents. I'm not going to give you very many of these. Let's see, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so suppose we had something like this. Okay, so 10 is still the longest chain. Okay, so this is decane. Complex substituents. Okay, what that means is we have substituents on the substituent. Okay, so this is the substituent, and it's located 1, 2, 3, 4, 5, 3, 4, 5, 6. Okay, so it's closer to this end. And then 5. The longest chain on this substituent is 1, 2, 3. Okay, so that's a propyl. Okay, we use parentheses. And this would be 1, 2, 2 trimethyl Okay, we put all that in parentheses. For this complex substituent, we start numbering from where it's attached. Okay, we don't worry about giving these the lowest number on the substituents within the substituent. Okay, so decane's the parent. This whole thing is on position 5. These are the 3 methyls are substituents on the substituent. Okay, so 1,2,2 trimethyl propyl decane. Okay, and as I say, you won't. I'm not going to give you very many of those. Okay, so this one with the 1-ethyl 2-methyl propyl group. Okay, and then this is a 1,1,3 trimethyl butyl group. Okay, and that would all be in parentheses. Okay, let's take a look at this one. Okay, so the longest chain, would be octane, which is shown in green. And the substituents, we have 4 methyls and an isopropyl. Okay, so this is 4 isopropyl. I comes before M, so we list the isopropyl first. Okay, so this is 4 isopropyl, and then every substituent gets a number, so it's 2236 tetramethyl octane. Okay, okay, here's a couple more complex substituents. Okay, so this is 3-ethyl, and then on 5 we have, okay, our longest chain is a propyl. We go this way, and we have an ethyl on number 1 and a methyl on 2. The 1-ethyl 2-methyl propyl, no name. Okay, so the parent compound will end in ANE, and then substituents will end in YL. Okay, we'll get to cyclic compounds shortly. We haven't covered cyclic compounds yet, but this is an 8-membered ring, so this is called cyclooctane. And okay, the reason we start here at number 1 is 113 is the lowest combination of numbers. So we've got 1, 1, and then this complex substituent is on 3. Okay, and that's in parentheses. Okay, so that's a butyl, 1, 2, 3, 4, and then we start from where it attaches, so it's 1,1,3 trimethyl butyl. Okay, so octane is an 8-membered alkane, and then cyclooctane is where we form a ring. Okay, boiling points of alkanes go up as we increase the molecular weight. Okay, so we start here with methane, and as we increase the number of carbons, boiling point goes up. Okay, notice here when we introduce branching at one end, Okay, we also have an increase in boiling points, but these isoalkanes are all lower boiling than the normal alkanes. Okay, so branching lowers the boiling point. The melting point also goes up, but notice that there's a zigzag pattern depending on whether we have an odd or an even number of carbons. This has to do with how the molecules will pack together in a solid. Okay, so alkanes with an even number of carbons have higher melting points than those with an odd number of carbons. Okay, one of the first slides we said that alkanes are primarily obtained from petroleum and petroleum byproducts and natural gas. Let's see, you probably haven't done this in lab. Imagine this will be one of your first experiments that you'll do. It's one that's called fractional distillation.
Pretty sure we'll start it tomorrow.
You've done that?
We're doing it tomorrow.
Oh, you're doing it tomorrow, okay. Yeah, fractional distillation. Simple and fractional distillation are techniques that separate compounds based on differences in boiling points. Okay, and this is the one of the major ways in which petroleum is refined. You don't get pure compounds, but you get groups of similar compounds. Okay, so to say that fractional distillation purifies, that's not correct because you get a variety of different compounds. Another important process that goes on at the refinery is called catalytic cracking and hydrocracking. Okay, the first is an example of hydrocracking. Okay, this introduces hydrogen, and if you heat a long alkane, okay, such as C12H26, with hydrogen and a catalyst, you'll get shorter alkanes. If you crack it without hydrogen, you'll get an alkene with a double bond and an alkane. Okay, commercially, this is a very important process because consumer demand for gasoline is much greater than all of the other products that you get from petroleum refining. And in fact, it was, this is not a recent phenomenon. In fact, as long ago as the late 1920s, fractional distillation alone could not keep up with the demand for gasoline. And so they take these longer chain alkanes, there's less demand for these. There's also useful products that we get from these, like diesel and jet fuel, but the consumer demand for gasoline is much greater. So in addition to what they call straight run, which is what they get directly from distillation, they also produce a lot of gasoline from cracking. And the catalyst is proprietary. The refining companies won't disclose what that is. Okay, so these are the fractions that are obtained from distillation of crude petroleum. First, we have the gases. Methane, ethane, propane, and butane, as well as some isobutane. And this is used for mainly for heating. Then we have gasoline. Gasoline, okay, it says 4 to 9 carbons, but this will vary a little bit depending on the season. On cold weather, it would be probably closer to 4 to 9, and warmer weather, you'd have just a little bit larger. Okay, maybe 6 to 11 or 6 to 12, but it'll vary depending on the season. Okay, kerosene is a higher boiling fraction. Then we have diesel, heavy oils, lubricating, and then we have paraffin wax, which is a solid, and then the residue that doesn't boil off, okay, that's left down at the bottom, that is asphalt. And some oil companies will crack their asphalt in order to obtain more gasoline. Okay, so these are separated based on boiling point. And these are actually, as I said, these are not pure compounds, but they're within a boiling range. Okay, so we have about 5 minutes remaining. The next topic that we'll look at is shapes of molecules. These are some methane representations. Methane has a three-dimensional tetrahedral geometry. This is the ball and stick in the middle. Okay, this is the representation that we use in 2 dimensions. The solid lines indicate those CH bonds are in the plane of the paper or the screen. Okay, the wedge is in front of you, and then the dash is behind. Okay, this is what's called a space-filling model on the right. The space-filling model accurately represents the size of the electron clouds, the relative size of the electron clouds. Okay, here is ethane, okay, with the stick and the space-filling model. Here we have 2 tetrahedral carbons, and okay, so this is a model of ethane, and I will zoom in on Zoom so hopefully you can see that a little bit better. Move it over one other way. Okay, so this is ethane, and we have free rotation about this single bond. And these positions that occur in free rotation are called conformations. Okay, so for example, looking along that carbon-carbon bond, we see that these CH bonds are lined up. Okay, if I rotate it this way, this CH bond bisects the HCH angle in back. Okay, like that. Okay, these are what are called conformations. They're actually not isomers. We can't separate these different conformations. There's constant rotational motion at room temperature. Okay, so this is ethane again, and this is a perspective drawing where we look at it from the side. And then on the right is what's called a Newman projection. Okay, in the Newman projection, we're sighting along that carbon-carbon bond, and the carbon in front, okay, we've got 3 CHs, and we start drawing those from the center of the circle, and then the ones on the back, we draw those from the outside edge of the circle. Okay, so this is one of the conformations of ethane. This one happens to be called staggered. And then if the CH bonds are lined up like this, okay, this is called eclipsed. Okay, so just like in astronomy where one celestial body covers up another, okay, this CH bond is covering up this CH bond. Okay, this is the least stable form because you have what's called torsional strain. You have electron-electron repulsion in the eclipsed form of ethane. All right, so here is propane. And for the Newman projection of propane, we sight along the bond between carbons 1 and 2. And that CH3 is on the back carbon. Okay, so this would be, okay, so that would be the staggered Newman projection for propane. Okay, instead of a hydrogen, one of the H's is replaced with a CH3. Okay, so we're out of time, so I'm going to go ahead and close now. Okay, and I will see you on Wednesday.